Hello. Today we will study an interesting way to perform calculations in special relativity. We are going to explore the so-called K calculus. Invented by Hermann Bondi. Okay, so let's start with our usual Minkowski spacetime. This is the special coordinate, just only one dimension, and this is the time. Okay. If I want to, we know that if I want to represent on this diagram the motion of a body traveling in a straight line with a constant velocity v, I draw simply a straight line like this. Oops, not very straight. Let's do it again. Okay, and this is the suppose that it refers to our rocket moving in the space. So the one line of a man on the surface of the Earth is just this one. It's just the vertical line corresponding to the time. Because we know that if it is at rest on the surface of the Earth, it is not moving in the x direction, but the time is passing, and so it moves along this line here. What about the rocket? Obviously, this is the straight line corresponding to velocity v. This is exactly the line of the moving rocket. Okay. Well, so what we can say? Suppose that at a certain we know that at t terrestrial time t equals 0. The rocket is passing near the Earth, okay, and then it goes away along the x direction. Okay, suppose that at a certain instant of time, terrestrial time t1, from the Earth, a beam of light is sent towards the rocket in the x direction. Okay, so it's the beam of light, the photon, moving at the speed of light. So we know that let's say that this is the coordinate ct. So this is 45 degrees. Okay, we know, and the photon reaches the rocket at a certain time. Okay, and suppose that there is a mirror on the rocket, and the beam of light is reflected back to the Earth and arrives at the Earth at the time t2. Okay. Let's call this this position. Now we calculate what it is. This is the position on in the x direction where the beam of light touches the rocket. Okay. Well, you can see that the point, the length, the distance between the origin and the point P is just equal to the proper time tau, because considering the rocket moving along this line respect to the Earth, okay, if we stay at rest on board of the rocket, I mean the astronaut living on board of the rocket, experience no displacement in space because he's standing still on board of the rocket, and so the only one coordinate representing a movement for him is just the time passing. But the time passing for him is not the same time passing for the terrestrial person. So let's call this distance here, from here to here, c tau, where tau is the proper time on board of the rocket. Okay, so what we can say? We can say that for sure the length of the, let's call this O, the length OP in this triangle here is just equal to the length from here to here, that is equal to the time t1, okay, sorry, ct1, because it is a length, a special length. So this is equal to OP, the segment OP, is equal to T1, CT1 multiplied by a certain factor that I call K. Okay, but I know that OP, we have said that is equal to C tau. Okay. Okay, for the relativity of movement, I can see the situation also in this other way, from this other point of view. From the point of view of the astronaut at rest on the rocket, okay, he sees the Earth going away in the opposite direction with the same velocity v. Okay, and so we can consider that the segment from O to CT2, okay, will be equal, I can say that CT2, the length of this segment here, must be equal, for symmetry, to the length OP, that is C tau, times the same factor K, because the situation is perfectly symmetric. You can see quite well looking at the picture. I know that this length here is equal to this times multiplied by a certain factor K. For the same reason, this length here is equal to C tau multiplied by the same factor K. Okay? Well, at this point, we know that, simply, we know that you can see immediately that from these two equations, what I can do. I can take the value of CT from the first equation and I substitute here, okay, the value of CT is this, okay, and so I've got CT2 is equal to what? CT1 times K, this one, multiplied again by k. So the final result, I can divide, this is a product chain, so I can obviously simplify. Sine t2 is equal to k squared times t1. Okay, but I don't know yet. I don't know yet what this k is. Let's calculate k. Well, I know that the distance traveled by the rocket in this time here, okay, that is this is ct2 plus ct1 over 2 is the mean value between these and these, okay? This is the time, okay? And so the speed, the space here, so this distance here, in other terms, the x coordinate of this point here will be simply the product of the velocity v times multiplied by the time passed. The time is this. I don't need the c factor now, because this is the, okay, let's leave it here, but when I multiply by v, I need simply the time, that is the average time, okay? And this is exactly the x coordinate of the point p. Okay? Well, but the same distance is traveled by a beam of light, okay, in which time? In this time here, you see? In this time here, from here to here. Because this is the moment the photon leaves from Earth, and this is the moment, the time t, when it touches the rocket. So I have to calculate this time interval here. That is simply half of this interval here. But this is t2 minus t1. So if I do t2 minus t1 divided by 2, and I multiply this by the speed of light, I get exactly the same coordinate x, because it's the space traveled by this beam of light. So these two quantities must be equal. But I can use this relationship here to express t2 as a function of t1. So this quantity here will be v times what? T2 is equal to k squared t1 plus t1 divided by 2, and this is equal what? C times k squared t1 minus t1 divided by 2. Okay, well, let's write this here. And I cancel something. Okay. Well, this is, I can factorize t1, and this is v t1 over 2 times k squared plus 1, and this one is c t1 over 2 k squared minus 1. And these two quantities must be the same, because we've said that they are exactly the same distance, distance from here to here, calculated by with the movement of the rocket and with the movement of a beam of light. Okay, equating the two equations, I've got v over 2 t1 k squared plus 1 equal c over 2 t1 k squared minus 1. Okay, let's simplify. I can erase T1, both members, and what I get is just a very simple equation. That is, let me develop a little bit. I know that V, I distribute the product, V k squared plus V equal c k squared minus c. Then let me bring this member here on the other side and this on this side. So I've got that c plus v equals c minus v times k squared. And so k squared is equal what? Is equal c plus v over c minus v. So we have found a value for k squared just with simple considerations about the movement of the rocket and of the light. We can go on, and from here it is better to divide by c both numerator and denominator. So this is equal to 1 plus v over c divided 1 minus v over c, and let me multiply above up and down by 1 minus v over c. Okay, but this is again is equal to 1 minus v squared over c squared. Okay, and finally, I can cancel this. I extract I perform the square root, so k is equal. Remember that k is a positive number because is the ratio between two lengths. So I can keep just only the positive root. So k is the square root of all this stuff here. But when I perform the square root, I've got the square root of 1 minus v squared over c squared, that is the Lorentz factor, you recognize it, divided by the square root of a perfect square, is just like this. Okay, so this is the value of the k factor that will be very, very important and useful to calculate many things. As a first example, we want to use the k factor to calculate the ratio between the Earth time and the proper time on board of the rocket. We can do it as follows. First of all, let's cancel a bit of stuff here. And let me write our fundamental result here. Okay? Well, we said that at the terrestrial time t1, a beam of light is sent by the man on the Earth towards the rocket, and he reached it at the event, the point in the space-time p, okay, after a time t1 plus t2 over 2 in terrestrial time, right? Because this is t1 is the moment when it leaves, and t2 is when it arrives back to Earth, reflected. So the moment when it touches the rocket on the Earth, okay, correspond to the time t1 plus t2 over 2, okay? I don't write the c factor in front because here I intend exactly the time, not the space corresponding traveled by the light, but exactly the time. Well, now using this relationship here, I can say that this time here is equal to t1 plus k squared. t1 over 2 is equal to t1 over 2 times 1 plus k squared. Okay, but this time here is the terrestrial time that I can call it t, okay, for instance, and it corresponds exactly to the rocket time, the proper time on board of the rocket, tau, because this is exactly the time when the beam of light touched the rocket. This is as measured by Earth, and this is, and tau is measured by the astronaut. So this is equal to what? It is equal to, we know that tau is equal to what? It is equal to k t1. You remember? This is t1, this is tau, and the factor k applied to the distance t1 gives us tau. Okay? Good. Well, from here, I've got that t1 is equal tau over k. And let me substitute this value here inside the first equation. So we have got that t, the terrestrial time, is equal to tau multiplied by 1 plus k squared over k. Okay? Sorry, I forgot a factor 2. Okay? Well, now I can use the expression of k and I substitute it in the last equation. Okay, this is quite a little bit boring, but this tau over 2 times 1 plus k squared. So it is 1 plus 1 minus b squared over c squared divided 1 minus b over c, all divided by what? All divided by k. Let me. I prefer before to do this. I work on leaving k without substitution for the moment. So this is tau over 2, and this is multiplied by what? 1 over k plus k. Let's see if this is a little bit better. I'm not sure. I'm not sure. Let me see. No. Probably yes. Let's do like that. Okay. Now I substitute k, and I've got tau over 2 multiplied by 1 over k, that is the inverse of this, 1 minus 2 over c divided square root of 1 minus v squared over c squared plus k plus the square root 1 minus v squared over c squared over 1 minus v over c. Okay, if I work out the common denominator, that is 1 minus v over c times square root of 1 minus v squared over c squared, and here I've got this divided by the square root. I've got this term here to multiply by this. The result is 1 minus v over c squared plus the denominator divided by this. I get the square root multiplied by square root. The square root goes away, so it is plus 1 minus v squared over c squared. Well, now this is equal to t. So t is equal all this stuff here, but I can develop the square of this term, obtaining 1 minus 2v over c, the double product, plus v squared over c squared, plus 1 minus v squared over c squared. Okay, all divided by 1 minus v over c times 1 minus v squared over c squared. Okay, well, there was a tau over 2 multiplying equals like that, equals tau divided by 2, that multiplies everything. I forgot, so this is like this. Okay, now here these two terms cancel, and I've got 1 plus 1 is equal to, and then I can write this t equals tau over 2, 1 plus 1 is 2 minus 2v over c, so I can factorize 2, that is 1 minus v over c, all divided by 1 minus v over c square root 1 minus v squared over c squared. Okay, 2 and 2 goes away, these they go away, and so at the end I have the terrestrial time t is equal to the rocket time tau divided by the square root of 1 minus v squared over c squared. So as you can immediately see, we have got again the time dilation expression, because from here I've got that the proper time tau is equal t multiplied by the square root of 1 minus v squared over c squared. And this is the well-known, already found expression for the proper time on board of the rocket compared to the terrestrial time t. Okay, I think that it's time to stop now. Thank you, and see you next time. Bye-bye.